you so much, everyone. You're all troopers. We're well into the home stretch. It's only 30 more minutes we can do, or 45 more minutes we can do this. But I'm Tyler Imfeld. I'm a PhD candidate at the University of Minnesota, and I'm really excited to share some of my dissertation research with you today. So I shouldn't need to convince anyone in this room, being in the macroevolution section, that among clade comparisons can allow us to disentangle and perhaps shed some light on evolutionary processes generating biodiversity, especially when we compare across clades that may differ greatly with regard to their diversity, either the number of species or the morphological diversity of those species, right? So something is going on when we compare this sister lineage here, Zygentoma with about 400 flightless species, to Pterygoda, their sisters, which have well over 1 million described species, right? And so comparing among clades allows us to work with these fairly general models that might explain the variance we see among multiple lineages rather than just two. So broadly, if we look across lineages, we may expect to find that the older lineages, the more species it's going to contain, right? And also assuming that that species diversification is constant among these groups, this relationship should be uniform, perhaps with some noise around that, around the number of species. But if we ever detect any outliers there, perhaps there could be something very interesting. If a group is more or less species rich given its age, perhaps there might be something going on. And folks frequently look at the phenotypic traits, and in particular the morphological traits of these lineages, to perhaps dive into that question some more. And there have been various explanations and causative, or relationships proposed. So it's been proposed that morphological disparity within and among lineages accumulates as a function of that lineage's age. It's also been proposed that it increases as a function of the number of species in that lineage, right? But based on theory, we know that both of these statements should be true. So if you have this simple 3-taxon tip with some branch lengths, right? Assuming that traits are evolving under Brownian motion in this, which we have a lot of evidence to suggest that many traits do, the total disparity of the traits in this lineage is simply equal to sigma squared, the rate at which those traits are evolving, and the total tree length, i.e. the sum of the branch lengths, right? And the total length of that tree is itself a function of how old that tree is, i.e. the age of the lineage and how many species are in it. And to show this proof of concept and to demonstrate what this looks like, I did a quick simulation study generating pure birth trees with variable ages, simulating trait data with realistic rates of sigma squared that I gleaned from analyses I'll show you later on. Under Brownian motion scenarios, I calculated the disparity of those traits on each tree, fit a PGLS model, integrating the age, the number of species, and the disparity of those traits, and repeated 100 times, you get a cloud of points like this, where each of these smaller ones is an individual tree with its constituent data set. The larger ones are the median across each time slice. And you can see this relationship where the number of species and the age of a lineage are interacting to cause this plateauing relationship between morphological disparity. So there's a diminishing return, so to speak, as you get older and more species rich, right? One last thing I want to point out about this is, so fitting this model using this interaction ended up being nearly equal to just using the total tree length, which is exactly what we suspect. Cool. So we have an idea going forward that we can use these two measures, extant richness and age, as proxies for total tree length when we, say, don't have a complete molecular phylogeny from which we can reliably calculate that, and we have an expectation of what this relationship should look like. And so given these basic models of species diversification, morphological disparity, how well do they actually fit real data? And so we can investigate whether these processes are uniform among lineages, and in particular, I'm interested in replicate continental lineages. And so in order to tackle this, I thought long and hard. I needed a species-rich group. They should be geographically delimited in that we want something at a scale larger than a single island, but smaller than, say, the entire biosphere. And we should be able to estimate the extent species richness of that group and the relative clade age, in addition to some estimate of their morphological disparity. And the critters that fit this bill, so to speak, are the New World Aussians. And to orient the poor souls that don't think about passerines every day of their life, here's a simple phylogeny showing the 3 major clades in the avian order Passeriformes. The cotton ball New Zealand wrens at the bottom, the sub-Aussians in the middle, and then the Aussians up here at the top. And I want you to take away 3 things about the Aussians here. One is that there are about 3,700 species and counting. That's over a third of all avian species are Aussians. And there's a tremendous amount of morphological disparity that we see in this group, morphological diversity. So everything from enormous crows to swallows, nectar feeders, seed crushers, the sky's the limit here, so to speak. But also, if you look at the phylogeny in this group over here, in red, it shows their origin is in Australia or Australasia. And so then if you look at regions, say like North or South America, the New World, all of the Aussians that are represented there today had to disperse into this biotic region from an ancestor in the Old World or evolve from an ancestor that did. And so part of my dissertation is involved looking at the published phylogenies containing and comprising all New World Aussians, and rather than this this assemblage of over 1,200 species arising from a handful of dispersal events, we've actually found evidence for over 44 dispersal events have generated the diversity of New World Aussian lineages. And a lot of these are kind of, depauperons, so to speak. So 17, almost a third of these have generated only a single species, like Parasaurus, Saltroparis, or Aroparis. But there's a tremendous amount of diversity, orders of magnitude. One lineage in particular, Embryozoidea, has generated over 800 species since it dispersed into the New World. This is really, really interesting. So we have a ton of lineages that are species rich, and there's a lot of them, and they're all contained within this biotic realm of the New World. And even better yet, there's a phylogeny that contains all of these species in a common relative timescale that was published by Yetz and colleagues in 2012, specifically looking at this chunk of the tree with all the Aussians on it. A lot of this tree was resolved using taxonomy, though, and was missing some species that weren't placed with sequence data. So we can't use total tree length estimated for each of these lineages on this tree, but we can estimate the age of those lineages. And we know the number of species that they have, and so we're able to generate that plot, right? So, if we look at the stem age here and the species richness, and then use an optimized maximum likelihood birth-death model to these lineage-specific data, we get a relationship like this, where the red line is that relationship, the gray lines are the confidence interval around it, and each of these black points are one of our Aussian lineages. And so you can see there's a lot that are on the line, a lot that are near the line, several that are within the confidence interval, but there are several weird things going on here, right? So unsurprisingly, all of our depauperons are down at the bottom. If you're only represented by a single species, you have not been very successful in the species diversification lottery. However, there are two other really interesting outliers I want to point out here. Embryozoids, our super diverse group, are substantially more species rich given their age than you would expect if this species diversification was uniform among these lineages. Whereas Tiliogonatidae, the silky flycatchers, are only represented by 4 species and yet are comparably old, right? So tie this back to our expectations. Yeah, there does appear to be a lot of consistent species diversification, but with a ton of outliers, right? We have some really, really wonky groups here. And are these lineages that are more or less species rich also more morphologically disparate or less morphologically disparate? How is this all related? And so to tackle that, I went to museum collections across the country, including my own institution, the Bell Museum at the University of Minnesota, measured a couple thousand museum specimens collecting ecologically relevant morphometric traits spanning nearly 86% of all described Aussian species. And to make that data set a bit more tenable, we ran a phylogenetic principal component analysis and retained 4 significant phylogenetic principal components that collectively explain greater than 90% of the total variance among all these traits. And then when we project all of these individual specimens into a phylomorphospace with built on 3 axes of shape variance rather than size variance, we get a plot like this. Ooh, spoilers, sorry. So each of these axes right here is a phylogenetic principal component. It's a major axis of shape variance among New World Aussian species. And this is great, we could talk about all this, but I want to talk about this. This is very interesting. If you look on a lineage by lineage basis, the occupation of this morphospace is extremely variable. So embryozoids here, right, are super old, super diverse group, is occupying over 50% of the entire morphospace that the entire Aussian assemblage has realized in the New World, right? And this is not the case at all when you look at other lineages that are either younger or more species or less speciose. None of the other groups, so these are the next 4 most disparate lineages, you see that none of them come anywhere close to occupying the same amount of space. The wrens and gnatcatchers kind of have their own neck of the woods, as do swallows, and then mockingbirds and jays, right? So there's a ton of variance here in the extent of morphological disparity in the occupation of morphospace among these lineages. And so does the age and the species richness of these groups actually predict that? Can we model it the same way? In theory, we should be able to. So What I did is quantify the disparity of each of these lineages rather than doing a convex hull, which may miss out on some of the geometric complexities of how these traits are or how these specimens are actually laid out in trait space. I used a hypervolume approach, which can account for holes or concavity in the data, and did this in a four-dimensional phylomorphospace, so calculated a four-dimensional hypervolume, and then transformed it by taking the geometric mean of size and shape variance, used that as the response variable in a PGLS model in which we use crown age and species richness as the predictors. And what's really cool is we do get the best supported model determined by AIC has an R squared of 0.8, which is not that bad, and it does have crown age and species richness as co-predictors with an interaction, i.e. the total length of that tree, or the expected total length of that tree, really closely matching or predicting the morphospace occupation here. But the shape of this relationship is very different, right? So think back to the blue plot I showed you in a second, and well, I'll just pull it up right now. So you see here, the shape of this relationship is actually inverted, right? So in the right, on the red plot, here again, you have age, number of species, and the disparity. These points that are both species rich and very old have disproportionately greater morphological disparity than if there was just a uniform plane describing this relationship. Until the gonadids are kind of down over here, so this regression surface almost resembles a kind of saddle, if you will. So it swings up and curves to the side, and you get exactly the inverse of that in our observed data. And I will point out that we tossed out gonadids and emberizoids just to see if our species diversification outliers were affecting this, and they don't at all. So I'm not going to show it to you because it's exactly the same, which is neat. So we find that in spite of outliers, we do detect this relationship among the total tree length and the number and the morphological disparity. But why is it opposite here? And to test how significant that is, I redid those simulations, 1,000 times, and so what you're seeing in gray are the distributions of those actual model parameters from the PGLS. So left to right, we have a term for the age, the number of tips in the tree, and their interaction. Two of these are significantly different between the observed and the simulated data, and in fact, this interaction is where that difference happens, right? So you can see the simulated data are nearly always negative. Very, very rarely are they positive, which is where you get that upswing, that saddle-like shape to the regression. So why are there such differences here? Why is the evolution of morphological diversity deviating so strongly from what we'd expect given neutral processes within these groups? It could just be that Aussie morphology is evolving under models or is not evolving according to Brownian motion. Alternatively, there could be variation in the rates at which each of these individual lineages are evolving. And this I want to unpack a little bit more of because this could possibly be shedding light on the fact that ecological speciation is underpinning a lot of this diversification, right? So look at emberizoids, our big winner here, very old, very species rich, tons of morphological diversity, but compare that to a lineage that's comparably old, but very species poor, with very little morphological diversity. Perhaps these processes of species diversification and morphological evolution are working in concert, and if you aren't capable of exploiting new parts of your ecosystem and generating morphological disparity, you're just going to be pigeonholed and become a depauperate lineage. So some takeaways I hope you remember going into the super social in just an hour and a half are that species diversification is not uniform among lineages, nor is the occupation of morphospace among all of these lineages. But the variance in this morphospace occupation is well fit, according to our expectations, by the natural log of the species richness and the age of those lineages. But the actual shape of that relationship is inverse. It differs strongly from what we'd expect given null or Brownian motion expectation. So ultimately, I'm out of time. Come find me if you have any questions. Thank your local museum for curating collections and making research like this possible. So thanks, y'all.